Okay, so on 8.3 we're going to talk about rational functions and their graphs. And I've asked you to look at the bell work and work the bell work. And you've been working on this. I ask you to graph these equations and to describe transformations and describe the asymptotes. I'm not going to go through all these because we've lost so much time already. But we've learned from when we first started 8.3 that this right here is just this function, y equal 1 over x, which now you can graph pretty quickly, right? 1, 1, and then at 4 and 4, right? You can graph those pretty quickly. Whoops. There you go. And we've learned that it's that, but because this becomes my a value, right? Which if it's greater than 1, it's a stretch. And if it's between 0 and 1, it's a shrink or a compression. So the stretch is like if you pull each end of this out, like if it's a measuring tape and you're pulling it out, this is going to go out this way. So you get a more narrow curve. Less of a curve, I should say. And then for a shrink, you're going to like push in on each of those ends where it will fall deeper into this crevice of the origin there. Okay, so we learned about that first. Then yesterday we learned about the translations, the h and the k values. What happens when we have an h and a k value? And we learned that, well, for here, that plus 2 is going to take that here, stretch it by 5, so it's going to be stretched out by 5, and then it's going to shift this over. Let's see, that's an, I can't read it now that I marked over it. Okay, so it's a plus 2, so that would have to come from x minus h, so that means the h must be a negative 2, and then my k is the negative 7 because it's x minus h plus k. So k becomes negative 7, h becomes negative 2. So we take this, we shift it to the left 2 and down 7. Okay, and then that new origin, what was here, goes all the way down there. And so everything from there goes like that. So what happens when we do this is we get a new asymptote out of this. We get a new vertical asymptote. And that becomes at, let's see, x equal, and where did we go here on the x-axis? We went back 2, so negative 2. So that gives us our vertical asymptote. And then to get my horizontal asymptote, we went to negative 7. So it's y equal negative 7. Right, so there's your new asymptotes. And that's basically everything in a nutshell from 8.2. Now we're going to move on about what happens when we have graphs that are not continuous. What's the difference between this and, actually let me just add a new screen. So what's the difference between these two graphs? So we look at this, and this one has a break in it, like a hole. We'll just say that's at 1. So where did this come from, and why do we have nothing graphed at 1? We've got a break in this. So it's not a continuous graph. This would be a discontinuous graph. This one, without any breaks, is a continuous graph. So what makes these holes in the graphs? And that's our focus today. Now, let's watch a quick video of our, I love the virtual nerd, she is so good. Let me go back. Oh, wrong one. Sorry. We'll do this one in a minute. The virtual nerd is what I'm going to look at. Okay, there we go. So we want to see what is a continuous function, and she explains this beautifully. So let's watch this.
what is a continuous function? To figure this out, let's start off by taking a look at these two graphs. Let's compare them to see what's different. Well, let's see. Taking a look at these two graphs, they look almost the same. This one, we see we have a line. Each x value has a y value. If we look here, this graph looks almost the same as the first one. But there's one difference. This area right here. There's a break in this graph. Here, we can see that there are no y values for the x values between 2 and 3. There, we don't have any part of our graph. There's a break in this graph. Since we have a break in this graph represents a discontinuous function. Now, this first graph doesn't have any of those breaks. So we can call this graph a continuous one. So now that we've seen an example of a continuous function, let's take a look at the definition. A continuous function is a function whose graph does not have any breaks or jumps. If there's a break or a jump in the graph, it's a discontinuity. And that represents a discontinuous function. So let's take a look at some graphs and see if we can identify if they are continuous or discontinuous. So let's say that we have this graph right here of our x and y axes, and we'll draw this graph. Now, does this graph represent a continuous or a discontinuous function? Well, to figure that out, we need to see if this graph has any breaks or jumps in it. If it does, it is not continuous. A good way to test this is to take your finger or a pencil and put it on the very left-hand side of the graph. Then trace the graph all the way to the right-hand side. If you ever have a spot where you need to pick up your finger or your pencil in order to move to the part of the graph that's next, then that's a break or a jump, and you do not have a continuous function. Here, we could take our finger or our pencil and trace the entire graph from left to right without ever picking up our finger or pencil. That means that this represents a continuous function. Neat. Now let's take a look at another graph. Let's say we have a graph that looks something like this. Is this graph continuous or discontinuous? Well, again, we need to see if there are any breaks or jumps. So again, take a finger or your pencil and put it on the very left-hand portion of the graph. Then trace. If we trace this graph, we get to a spot where we would keep going down forever and ever. But there's more of the graph over here. In order to get from the part of the graph that we're on to the next part, we need to pick up our finger or pencil and put it on that next part of the graph in order to trace the rest of it. This graph does not cross over the y-axis. We have to pick up our finger or pencil in order to trace the entire graph. Since we had to do that, there is a break in the graph. That means that this graph represents a discontinuous function. Okay, let's take a look at one more graph. Let's say we have a graph that looks like this. Is this graph continuous or discontinuous? Well, again, let's see if there are any breaks or jumps. We take our finger or our pencil and we start tracing our graph. And we get to a point where we need to pick up our finger and put it back down in order to continue to trace the graph. And we have another spot right here where we have to pick it up. Here, there are two jumps in this graph. Two spots where we need to pick up our finger or pencil in order to get to the next part of the graph. That means that this graph represents a discontinuous function. Now, in some math classes, like calculus, the definition of a continuous function may become a bit more specific. But for now, just know that a continuous function is a function whose graph has no breaks or jumps.
Nice. She does such an amazing job, and that's why she's the virtual nerd. Okay, so let me do this. Okay, now remember, you have access to all these, and I put a code out there, the website. I put the link to the website to get here and gave you a login and a password to get to all these. And this is just one of the things that are available to you out there. Actually, I looked at the other videos for this lesson, and they weren't as straightforward as I wanted them to be. So let's go back to our lesson. All right. So now, on your whiteboard, whoa, you don't have a whiteboard today. Make sure you grab a whiteboard every day, guys. They put them up sometimes at the end of the last class. So if you don't have one, always grab one, because we will use them a lot. And I was going to have you draw a continuous and discontinuous function. And if we can, let's talk about what kind of things make a graph discontinuous. So let's start looking at what kind of functions do that. Well, rational functions can certainly do that, which is what we've been working with. Now they're going to say, okay, we've been having pretty simple rational functions with, like, you know, we've got an a on top and the x minus 5 plus 7, something like that, right? And let's say maybe a is an 8. So we've been having pretty simple things. But what happens when this numerator up here starts becoming more complex, or our denominator becomes more complex? More complex being that, okay, now maybe we're just going to put polynomials up there. And then, you know, from polynomials we'll start factoring. And from factoring we'll start canceling things out and rewriting things. But what happens is along the way we learn how to construct a pretty intricate graph in a very easy way. And this is how we do it. So when you get a rational function now, it could be more than just, like here you've got a binomial, x plus 3 on the numerator and x plus 16 on the denominator. So it just says you use a ratio of polynomial functions. Ratio meaning it's division, and you've got something more complex on top and something more complex on the bottom. Okay? So if a function has polynomial in its denominator, its graph will have a gap at each 0 of this denominator. So what makes this 0? When x is equal to negative 16. I heard 16, but be careful of the signs. And I know I marked this up, and it's probably hard to read all over the class. And we've got to push all these chairs back. I didn't do it yesterday because of the people in here. I knew they'd be circulating, but the closer you are, the farther to the side that you get, the harder this is to see. So when I push you guys back, you can see it better. So, all right, so we know at x equal negative 16, we're going to have a break in this gap because it's undefined. This fraction would be undefined at 16, or negative 16, excuse me. So if that was a straight line, I'm not saying it is, but let's just play like this graph is a straight line. When we get to, when we get to, let's say negative 16's right here. So when it comes up, we're going to have a break in the graph, right? So it's x is undefined there. It doesn't exist. It's not allowed. So it causes a break in the graph. Any questions about that? Well, what if I had a trinomial down here that they ask us to factor out, and we end up with two binomials, like x plus 2 and x minus 6? Well, then you're going to have two breaks in the graph. See where this is going? So these breaks could be a one-point hole in the graph, like what I've been showing, or it could be something as complex as an asymptote. Okay, a vertical asymptote. So here's some examples. So is this continuous or discontinuous? Continuous, because there's no breaks. How about the next one, the middle? Discontinuous because it's got that break right there, the hole. And how about the last one? Definitely, because you had to pick up your pencil to move to the other side of the graph. Now let's take a look at what's the difference in these. So why did this one not have any breaks? There's a denominator. Our denominator on the first one is x squared plus 1. Well, is there anything here that can turn this to 0? No, because we can't square any number in this world and make it come out -1. Not with our math rules, okay? So even if you try to put in a -1 there, well, -1 squared is a +1. And then you're going to end up with a 2 down here. So there's nothing in here that makes that 1, or makes the denominator go to 0. So that's why there's no breaks. Okay. Now in the next one, look, in the denominator you've got x plus 2. So what makes that 0? -2. Oh, wow, that's right where that hole is. At the x equal -2, there's a hole. See that? And then for the last one, look at your denominator. You've got x minus 2. So what turns that to 0? A +2. So we would expect at +2, and each one of these units are 2, 2, 4. Okay. So right here, we don't have a hole. We've got a whole vertical asymptote. So how do you know which one's the hole or an asymptote? So we'll see. All right, and this is what we just talked about, so I'm not going to go over that again. Now, points of discontinuity, these points can be removable or non-removable. And here's the down and dirty, quick and easy way to tell. If I had y equal x plus 4 over x minus 2, well, that's a binomial, and this is a binomial. There is nothing I can factor out, right? So I know that I've got a point of discontinuity that no matter what is going to be there at x equal 2. So that's a non-removable discontinuity. What makes it removable? Well, what if I had this up here? What if I factored something out and it ended up x minus 2 times x plus 4 over x minus 2? Well, look, these would actually cancel out. Because this can be canceled out, we call that x a removable discontinuity. Because you could factor it out and get rid of it. That becomes a removable discontinuity. So that's all there is to it. If it can be factored out, it's removable. If it can't be factored out and it just stays there, it's non-removable. Okay? Excuse me. Your factors of your denominator will reveal your points of discontinuity, and that's what we've been saying every one of these slides. It's over and over. We're saying the same thing but in different ways. So when you're looking for discontinuities, you first want to make sure everything is factored as simple as possible. Once it's factored, then you want to look for what can be factored out. What can be factored out becomes a removable discontinuity. What stays after you cancel things out becomes a non-removable discontinuity. So let's look at our first problem. And this one goes with in your assignment on 8.3 problems 1, 2, and 3. This is on the test. So we need to know how to do these. It says, and this is a loaded question, so there's lots of parts to it. And this has like A, B, C, and D. There's like 4 different examples that go with this. What are the domain, the points of discontinuity of each rational function? Is it removable or non-removable discontinuity? And then what is the x and y intercepts? And I haven't talked about those yet. I'll just teach those as we hit it here, okay? I had a slide, but I deleted it by accident, and I haven't had a chance to put it back in. So I'll just teach it as we get there. So domain, let's look at the problem first, and let's see what they're giving us. Y equal x plus 3 over x squared minus 4x plus 3. Well, right off the bat, I see that quadratic, and I need to factor that baby, right? So I'm going to say, what 2 factors of 3 add up to be -4? Well, it would be -3 and -1, because when they're multiplied together, you get a +3. When you add them, you get a -4. So we know those are our numbers, so it's going to factor into x minus 3 times x minus 1, okay? So let's do that. And there it is, highlighted there. right there where I checked. So that's the first step. Always factor your numerator and your denominator, but your numerator was already simplified. So now let's see, can we cancel anything out? Nope, because you've got an x plus 3 as a numerator and an x minus 3 in your denominator. So you can't cancel anything out. So let's go back to what they ask us. What are the domain? Okay, well first we have to figure out, in our domain, it means what can x be? Well, it's easier to see what can x not be. X cannot be what here? A 3, or x cannot be a 1. So you're going to say the domain is all real numbers except for 3 and 1. Do you not have a book for notes today? Do you want me to take notes? What? Oh no, what hour do you have?
Next hour.
Oh, okay, see you in a bit. Bye. Whoops, Twilight Zone. How embarrassing. All right. She's sweet. It was a big day for ROTC. They had big, like sergeants and generals coming in and reviewing everybody. What was it, James?
Well, there weren't generals, but it was an inspection.
Oh.
It was in the second hour, for most people anyway.
Okay.
There was also people who were presenting a PowerPoint for the service learning thing, which was the blood drive a while back.
So how did everybody do?
We did pretty good, I think.
Great.
Whether we still get to keep our gold star or not, I'm not sure.
I bet you do.
Hopefully,
Well,
yeah.
let us know. Well, you don't have to let us know if you lose it, but let us know that you get to keep it, okay? All right, so we know that this is, our domain is that easy, guys. You just look at what can x not be. Look at your denominator. X cannot be a 3, and x cannot be a 1. Because if it is, either of those numbers, we get an undefined value, doesn't exist. So what happens is we've got a hole in our graph, or we're discontinuous at those 2 points. So you say for domain, it's all real numbers except for x cannot equal 3 or 1. Okay? Now, when you look, I already stated, these cannot be canceled out. Nothing can be canceled out because you've got a x plus 3 up here and an x minus 3. Those aren't the same. You might think at first glance you could factor those or cancel them out, but they don't because the signs are different. So you say these are non-removable points of discontinuity. Okay. So now we've answered this, this, and this. Now we've got to talk about the x and y intercepts, which I said I'd just teach it as we hit it. So how do you get an x-intercept? The x-intercept, you just look at the numerator. What makes this numerator 0? When x is equal to negative 3, so there's your x-intercept. That easy, guys. So now we've got the x-intercept. So x-intercept is what makes your numerator 0. Now what about the y-intercept? It's just like everything else we've ever done. Turn all your x values to 0 and see what flies. Okay, so let's do that. For our y-intercept, turn all x's to 0, because that's all a y-intercept is, right? When x is at 0. You've got a y is crossing the y-axis when x is equal to 0. So you turn all your x's to 0, so there's that one, everything goes to 0, and calculate. So you get 3 over negative 3 times negative 1, which is 3 over 3, which is equal to 1. So there's your y-intercept. Y-intercept is 1. So that's how you get your x-intercept and your y-intercept. All easy things to do, there's just a lot of them. But once you do 3 or 4 of them, you'll remember. Okay? Any questions so far? I'd love to have whiteboards so I could give you a quick show me. So don't forget those tomorrow. The next problem, I told you this is 4 parts, so I'm going to speed it up here now. Now let's do the same thing here. Okay, so there's nothing we can factor. That's our first step. So let's see, the first thing was to tell us the domain and points of discontinuity. Okay, so domain depends on our points of discontinuity. Well, again, we're into that same thing where no matter what I put in here, I'm not going to get a negative number. So this is never going to be 0. So there are no points of discontinuity. This is a continuous function. So domain is all real numbers. Okay, so now they are, well, because we don't have points of discontinuity, we can't say they're removable or non-removable because we don't have any. So now let's talk about the x and y intercepts. Okay, so let's look at the x-intercept. Look at your domain. So what makes that 0 when x is equal to 5? So we've got an x-intercept at 5. All right, now let's talk about the y-intercept. Let's turn all of these x's to zeros. Here, actually, let me do that. So this goes away, and this goes away when you turn that to 0. So we're left with negative 5 over 1, which is just what? Negative 5. So our y-intercept is negative 5. Okay, so if it was a straight line, you could have already graphed it. It's continuous, and there it is. Okay. Any questions? Let's look at the last one. Or do I have 4? Oh, I only had 3. So there were 3 to this one. Alright, so now they're going to give us x squared minus 3x minus 4. There's that quadratic we can factor, right? What two factors of negative 4 add up to be negative 3? Negative 4 and 1. So we need to factor that numerator to x minus 4 times x plus 1. Right there it is. Over x minus 4. Now, let's first talk about our points of discontinuity in our domain. Well, points of discontinuity is when x is equal to 4. So our domain is all numbers except 4. Our points of discontinuity is x equal 4, but it's removable point of discontinuity because it can be canceled out. See the x minus 4 on top? Because it can be canceled out, it's removable point of discontinuity. Okay, so now that leaves us to our x and y intercepts. So now our x-intercept, look at what's left over when you cancel this out. What makes this 0 when x is equal to? You've got x plus 1, so x must be negative 1 to turn that to 0. So we've got an x-intercept at negative 1, so plot that. They didn't tell us to graph it, by the way. I'm just showing you the graph and how these work. And then the y-intercept, well, what are we going to do? We're going to turn all the x's to 0, so they all go away. And we get negative 4 times 1, which is negative 4, over negative 4. Well, that goes to 1. So we've got a y-intercept at 1. 1 and negative 1. So there it is. So you've got this line that goes all the way up through 1, negative 1, and then it's got a hole at 4, and then it goes on and on. See how to do those? Any questions? Okay. So your problems 1, 2, and 3 are like that. So you'll work those tonight at home. Now let's look at the next problem. Now, for problem 2, it's about finding your vertical asymptote. So when you have these things where they never touch, it gets really close but never touches. The vertical is the one that goes up and down. So if you were to describe it, it would be like, okay, x, if this is at, here's my origin, 1, 2, if that's at 2 crossing the x-axis, you would say, well, my vertical asymptote is at x equal 2. Okay. So how do we find those? And see, they're actually slowly giving us all the rules to quickly dissect an equation and graph it quickly. just by these rules. Oh, well, we know it's going to have a curve here, it's not going to touch here, it's going to go up and down, and that's where we're headed with all this. So how do we get the vertical asymptote? So what we want to do is we want to look at the powers. So we want to look at the powers. So this is the rule, and I'll put it up here for video's sake if someone wants to pause it and read it. But you're going to look at the highest power on the numerator and the highest power on the denominator. And those are the things we're going to pay attention to. So if okay. So let's do that. So look at our removable. So we've got 2 and 3 here, and then up. So these are going to be points of discontinuity. They're non-removable because we can't factor them out. So are any of these zeros of the numerators? What's the zero of our numerator? It would be 1. So none of these match. So both of these lines. I'm sorry, guys. When I started this off, I said you look at the powers. That's for the horizontal asymptote. We look at the powers. For these, you just look at the denominators. Sorry, I reversed that, and I apologize. So let me back up quickly. Just look at your denominators. What's these zeros? Can they be factored out? No. So both of these are asymptotes, vertical asymptotes. So that means you're going to have one at 2 and one at 3. So you're going to have one here, and you're going to have one there. So somehow there's going to be graphs coming in. I don't know how, when, or where. We don't know what the horizontal is yet. Okay, so it's at 2 and 3. So again, for the vertical asymptote, you just look down here. If it can't be factored out, then both of them become, you're going to have 2. Okay, so both 2 and 3 are vertical asymptotes. So now your 4, 5, and 6 are just like this. Find the vertical asymptote and the holes of the graph for each rational function. So, or holes. So this would be vertical asymptotes. Okay, now here we go with the horizontal. This is what I was explaining a minute ago, and I just got ahead of myself. For the horizontal, what you do is you look at the powers, the highest power in the numerator and the highest power of the denominator. We'll call the highest power of the numerator, let's just call this, ax to the m over a, we'll call that b, x to the n, okay? So you're going to look at the powers. If the power on the top is less than the power on the bottom, then it's got a horizontal asymptote of y equals 0. It's just your x-axis. Okay, so if the power on the top is smaller than the bottom, it's just the x-axis is your asymptote. Now, if m is less than n, there's no asymptote. Whoops, I didn't mean to do that, but it's okay. So if your power on the top is larger than the power on the bottom, there's none, no asymptote. So we've done this one and that one. Now the last one, when they're equal, so if like I had x to the third power over x to the third power, if they're equal, then you're going to look at the coefficients. So if this was like 5x to the third over 9x to the third, then your asymptote becomes 5/9. When the powers are equal, you just take the coefficients, 5/9. Okay? So let's take a peek. What is the horizontal asymptote for the rational function? So again, what are we going to do? The first step is to look at your degrees, the highest degree. So that's a first power and that's a first power. They're the same. So on those two that had the highest powers, that's like a 1x. So it's like 2x to the first over 1x to the first. Since the powers are equal, it's just going to be the coefficients. So 2 over 1, which is just 2. So it's going to be y equal 2 for our horizontal asymptote. So that means going through the y-axis at 2, there's your horizontal asymptote. Okay, so you look at the powers, the highest power. Look at the next one. On the numerator, our highest power is 1. On the denominator, our highest power is 2. So the top one is smaller than the second. So what was that rule about the top one being smaller? If it's smaller, then it's just the x-axis. So we would say the horizontal asymptote is the x-axis, which is y equals 0. And the last one, we're going to look at our powers again. Our highest power here is 2. The bottom one is 1. This is greater, the numerator is greater than the denominator power. So what did we say when it's greater? There's no horizontal asymptote. So there's no asymptote on the third one. Okay, so actually I got further with you guys today. Nobody else even made it to problem 3. So if you will, try to work through number 9. And anybody who watches the video at home tonight, work through number 9 tonight. We will finish this up tomorrow. Okay, so you guys are basically ahead of the other classes, so good job. Any questions? All right, this concludes our video. Thank you for watching. We'll finish this tomorrow.